Okay, we move on to the next topic. Okay, it's being called internal force convection. Okay, so this internal force convection, this different compared to the external force convection, whereby it will involve the outside flow. Okay, the outside flow. So this internal force convection is inside flow. Okay, inside flow, and it's also associated with the outside flow as well. Okay, so let's look at the theory. Okay, this equation is very important because they will detail out the relationship in between V average and M. Okay, M um, MD is basically mass flow rate. Okay, mass flow rate. Okay, and from M you can basically uh, know the value of V. Okay, so how do you know the value of V? This one. Okay, so you know that rho is equals to M over V, right? So V in here, okay, V titik, V dot is M over rho. Look at this equation. V average or V only lah, okay, is equals to M A cross-sectional dot rho. So it's basically V that dot over AC. So when you know the velocity value, you will know the M with the help of AC and rho, and also the volumetric flow rate. Okay? Sometimes you need that to convert from one value to another, or one unit to another. Okay, so you have to be well versed in terms of how do you want to convert from one particular, for example, V average, you want to turn out to be V dot or M dot. Okay, because it's very in need. Okay, very much in need. Okay, so D is the diameter, and mu is this one is not kinematic viscosity, it's dynamic viscosity. Okay, kinematic viscosity is mu, mu. Okay. Okay, classification of flow regime for inside or internal force convection inside the tube. It is a bit lower, okay, in terms of laminar, and turbulent is a bit lower as well, the range. Okay, if to compare with the previous external force convection, right? And then you have practical laminar is turbulent is more than 4,000. Okay, and for the surface roughness, the zero surface roughness, normally your Reynolds number will become uh, extended lah. Okay, lagi banyak. Okay, if the roughness, okay, roughness is equals to 0. Okay, all right. Let's go to the hydraulic diameter. Okay, why we need this hydraulic diameter? Because we want to determine the value of Reynolds number. Okay, so you ever want to determine the value of Reynolds number, you have to know the value of hydraulic diameter. Okay, because the Reynolds number formula is VD over nu. So D is referring to the hydraulic diameter. Okay, so it happened to be for circular tube, the hydraulic diameter is basically D, the diameter of the tube. Okay, for square duct, it is A. Okay, and for rectangular duct is this formula, and for channel uh, without the upper surface, okay, Just to compare with rectangular duct. Okay, this one is channel or sum. Okay, ataupun longkang macam longkang kan. Okay, ataupun salo lah, salo air tak ada bumbung macam tu. It's being called the term is 4AB over 2A plus B. Okay, the hydraulic diameter. Okay, and P is perimeter lah, so you don't have to determine this one lah. Normally, it is always in circular tube. Okay, unless it's stated in the question, right? Okay, this one is also just like on the external force convection. You have hydrodynamic, whereby it is Qs, constant Q, and this one is constant Ts. Okay, but the difference is that the no slip condition will be on two sides. Okay, it's the wall side. Okay, above wall and below wall. Okay, and of course the maximum velocity will be on the center of the fluid. Okay, this one is fluid. The center of the fluid, or sometimes you call it bulk fluid. Okay, so in here it's very important for you to know the value of entrance region or developing region or fully developed region. Okay, once you have established the boundary, okay, then you call it the region. That region is fully developed. Okay, under that region is developing region or entrance region. How do you know? You will have formula. Okay, and this one is just the same with the hydrodynamic, which is velocity. This one is temperature. Okay, the uh, farthest distance, okay, or the center of the fluid would be the highest temperature. Okay, as to compare with the um, surface. Okay, but it will depends on Ti here, Ti, okay, and Te. Okay, T initial or T inlet and T exit, okay, or Tn. Okay, so uh, this Ti and Te is referring to the fluid temperature. Okay, don't get confused. Ts is basically surface temperature, the material temperature. For example, this one is stainless steel pipe, so the surface of stainless steel pipe. Okay, this one is water inside, so it is fluid. Okay, Ti and Te is referring to fluid. Okay, so you will not get confused with that. Okay, so these two entrance region is very important because you have to determine the region in order for you to again, okay, you will determine the equation for N. You turn out to be H and you turn out to be Q. Okay, this is the orientation of this theory. Okay, one determine NU, and then you get H from that, and then eventually you will get Q. Okay, all right. Okay, for this one, I need extensive explanation. By the way, entry length. How do you know the entry length? You have to determine whether your region is laminar or turbulent. Okay, or whether you are basically will be hydrodynamic region or thermal region. Okay, so if your hydrodynamic region, this will be the simpler formula. Okay, and if you ever have the Prandtl number as an additional term in it, so you can have this thermal boundary layer. Okay, and for both for turbulent, it will be the same for both layer lah. Okay, it's 10D. Okay, I will show you after this. Okay, let's look at this figure for 5.13. Okay, if you look at the Nusselt number, you will have a Nusselt number of thermal and Nusselt number of hydrodynamic, Nusselt number of velocity and Nusselt number of temperature. Okay, at first, okay, they were slightly different. Okay, they were slightly different in terms of the Nusselt number at the entrance region. Okay, entrance region number is quite different, whereby you find that the hydro um, hydrodynamic is much more higher lah, okay, the Nusselt number compared to the thermal region, okay, thermal boundary region. And then once it goes towards the length of the pipe, okay, as to compare with the diameter, it will become fully developed, and the Nusselt number for T and H will be the same. This is justify why LH and LT is the same formula, which is at the point of 10 diameter, 10 times diameter. Why is that 10 times diameter? Because this is the least, okay, the highest diameter that needed, okay, to be fully developed. Okay, because if we look at other Reynolds number, they already achieve fully developed region, okay, even before 10D, maybe 8D or 6D, and this one is even 2D is already fully developed. But for this case, the maximum one would be this one. Okay, so that is why we end up with this formula. And of course, once it reached this for that particular Reynolds number, of course the other will already at that point as well. Okay, so that's why it ended up with 10D. Okay, but for the first region, the initial region or entrance region, so it can be this two formula. Okay, so the length of that pipe is very important. Okay, then you need to have determine whether the length is sufficient enough for that particular um, system lah. Okay, for example, if that system the length is 100 meter, for example, and the entry length is 50 meter. Okay, so of course, okay, that particular system is in fully developed region, because only need, okay, 10 50 meter for to achieve the fully developed regime, okay, or the fully developed flow lah. Okay, macam tu. I will explain to you in the example as well. Okay, no problem. Okay, so again, both Nusselt identical in the fully developed region. Okay, all right, for Q, okay, this would be the equation related um, to the internal force convection. Okay, so this is the general formula. Okay, this one is general formula for fluid, yeah. Okay, and this one is basically for surface. So do not get confused. Okay, so and then when they want to basically jumble up the formula, okay, it end up with this relationship, okay, in between TE and TI. Okay, so for this system, okay, you need to really be careful, because the QS over H, okay, HA lah pun boleh juga, if this one is QS, okay, this one is QS times A sebenarnya, okay, this one is QS times A. So basically the alternative formula is Q over HA. Okay, so you have to be very particular with this, okay, because this one is also an equation related juga. Okay, so at TI, okay, you will have a certain value of TS. Okay, and it will be developing up until when they reach the constant value. At this point, okay, starting this point, the fully developed region, fully developed L, okay, it will begin to be consistent in terms of the gradient of temperature, meaning that if the temperature of the fluid is increasing, it might as well increase in terms of the temperature of the surface. Okay, so if you look at this cylinder pipe, okay, at this point, okay, from this point, the temperature of surface and the temperature of the fluid, they are what you call bergerak seiringan. Okay, they move all together with a constant distance. Okay, this distance is basically Ts minus Tm. Okay, Tm is the material or that point material. Okay, Tm is the temperature at that point, meaning let's say you have point 2. Okay, so this point 2, for example, point 2, this is point 3. So the value of Ts at that point is that value. Okay, for example, this one is Ts2. So the value of this is Tm2. Okay, so that is mean by Ts. But at the exit, the value of M will become Te. At the initial value, okay, initial value, the Tm is basically Ti. Okay, so this is where you have a constant Qs. Okay, so you have to really careful when you read the question. You have to make sure that you know whether this is constant Qs or constant Ts, because the gradient will be different. The movement of Ts, if to compare with Ti and Te, is different. Okay, let's see on the next type. Okay, or you call thermal. Just now is hydrodynamic. Okay, oh, sorry, there's no place to put my face. Sorry. Okay, all right. For constant Ts, okay, if you look at the Ts is constant here. Okay, the one that is always in increasing is Ti, and plus it is increasing in not in the uniform trend. Okay, it is some sort of parabolic something like that. Okay, so it is better. That is why you need this kind of T log mean. Okay, to basically to determine the value of the temperature difference with regards to the conventional concept lah. Okay, so we tend to linearize this relationship. That is why you have data T log mean. Okay, so data T log mean is basically this formula. Okay, this one T delta Te is basically you know that it is Ts minus Te, okay, and you minus with Ts minus Ti, okay. So that is why the value of Ts is cancelled out, negative negative, Ti is in front and Te is at the back. So that is why it become like this. Okay, and then you have to some sort of know lah what is the value of delta T log mean. Okay, so and this one is the formula for Te if you ever know every temperature. Okay, and also H will depends on Nusselt number. Okay, how do you depend Nusselt number? Still depends on the flow regime and so on and so forth. Okay, so just like in the previous slide lah. Okay, region dia macam mana, kan, macam ni. Okay, aerodinamik ataupun tak. Okay, Okay. All right. Let's look at the example. Okay. Water enters a 2.5 centimeter internal diameter of thin copper tube at of a heat exchanger, okay, at 15 degrees Celsius, okay, at a rate of 0.3 kilogram per second, okay, and is heated by steam condensing outside at 120 degrees Celsius. Okay, so you know that the surface is 120 degrees Celsius. Okay, and you also know the Ti and Te. This one is Ti, this one is Te. Okay, determine the length of the tube. The length of the tube. Okay, so once you know the length of the tube, the area of the tube, and then you will know the value of the length lah. Okay, since dia bagi TE, TS and TI, so you can always use this value lah. So CP is being assumed as 4187. Okay, this one is a diameter, so basically the so-called the A, okay, the value of A is pi LD. Okay, jangan lupa. This one EAS pi LD. Okay, so what is the value of H? Okay, value of H is been given here, 800. A, we cannot know what is the value because we don't know L, right? So we're going to want to determine L. D is already know, okay? So we can use pi LD here. And you have to determine what is T log mean, okay? By this equation. TE, you know, already know 115, okay? TI, you know, is 15, okay? I think this one, TI is 15, this one is 115, TS is 120, okay, and so on and so forth. So you will definitely get delta T log mean, and this 2 is basically just plug in the equation. M is being given here, okay, but just to make sure that the unit is consistent. So Q is equals to Q, so HAS delta T log mean is equals to M dot CP TE minus TI. So all the value has been known. So you know this value, and this value, and this T log mean as well. Okay, and then you know this value, so you will get AS. Okay, so AS equals to pi LD. So D you already know, so L is equals to AS over pi D. Okay, so the answer is 61. Right? So that is the and I think you know that since you are using this A log mean, you know that the system is uh, constant TS, right? So you have 120 degree Celsius of steam condensing, okay, condensing steam, right?